Let us compare how simple interest and compound interest works. Suppose we have two dads, poor dad and rich dad. They both have 1,000 pesos to invest. Poor dad invests it at 10% simple interest. After a year, it earns 100 pesos as interest and the principal is unchanged. After the second year, his money earns another 100 pesos and reinvests the money he has for another year. After the third year, his money earns another 100 pesos, earning a total of 300 pesos interest. Together with the principal, he now has 1,300. The rich dad invests his money at 10% compounded annually. After a year, his money earns 100 pesos as interest. The new principal is 1,100. After the second year, his money will earn 10% interest amounting to 110 pesos. His money now is 1,210 including the principal. This in turn will be the new principal to be invested for another year. At the end of the third year, his money will earn an interest of 121. Including the principal, he will now have 1,331. Clearly, the interest earned in investing the money at 10% simple interest will give a fixed amount every year, while an amount invested at 10% compounded annually will give an exponential increase in the principal. This is the power of compounding. Whenever there is a chance for you to invest, choose an investment that offers compound interest. The simple interest is indicated by a straight line, provides a steady increase for the different rates 5%, 10%, 15%, and 20%, while the compound interest shows an exponential increase in the amount as shown by the curving upward of the graph as the number of years increases. The formula for the compound interest is F is equal to P times the quantity 1 plus R raised to N, where F is the future value, P is the principal, R is the interest rate per year, and N is the number of years. Consider the problem. Heather invested 12,000 for 5 years in an account earning 7 1/3 annual compound interest. How much would she expect to collect at the end of 5 years? From the formula F is equal to P times 1 plus R raised to N, we have P is equal to 12,000, N is equal to 5, and R is equal to 7 1/3%. Written in decimal, that will be equal to 0.0733. Computing the value of F will give us 17,094 and 42 cents. Thus, Heather is expecting to collect 17,094 and 42 cents at the end of 5 years. Finding the current value. The formula P is equal to F all over 1 plus R raised to N is the current value. Consider the problem. An amount of 5,000 is to be inherited in 4 years. How much would it be if it is cashed in now, given that the interest rate is 6 3/4% compounded annually? From the formula, we have F is equal to 5,000, N is equal to 4, and R is equal to 6 3/4%, written in decimal as 0.0675. Computing the value, we have P is equal to 3,850 and 33 cents. Thus, the present value of 5,000 is 3,850 and 33 cents due in 4 years. What is a discount factor? A discount factor is a quantity being multiplied to the future value to get the present value. It is determined by the formula highlighted by a purple color. This quantity will be called a discount factor. Suppose the inheritance problem were to be cashed in under the condition A. The interest rate goes up to 8%, but the time stays the same. We have DF, or the discount factor, is equal to 1 over 1 plus 0.08 raised to 4, which is equivalent to 0.735. Multiplying this discount factor with F, we will get 3,675 and 15 cents. For letter B, the time extends to 6 years, but the interest rate stays the same. We have the discount factor is equal to 0.676. Multiplying it with 5,000, we will obtain 3,378 and 80 cents. For letter C, the interest rate goes up to 8% and the time is extended to 6 years. We have 1 all over 1 plus 0.08 raised to 6 is equal to 0.63. Multiplying that with the future value of 5,000, we obtain 3,150 and 85 cents. As the time is held fixed, the discount factor decreases and the present value P decreases as the rate increases. We can conclude that while the discount value P changes positively with the DF, or the discount factor, it has a negative relationship with both the interest rate and the term of discounting N. The compound interest rate can be found in terms of all other remaining factors in the compounding formula F, P, and N. If you want to buy a car for 1,548,500 in 5 years, but you only have 770,000, you want to invest it to raise the amount you need in 5 years. What should the interest rate be? We have N is equal to 5, F is equal to 1,548,500, P is equal to 770,000. Then, plugging it in our formula, we have R is equal to fifth root of square root of 1,548,500 divided by 770,000 minus 1, that is equal to 0.1499, or approximately equal to 15%. Finding the compounding term. The term N can also be obtained in relation to all other compounding factors. The formula N is equal to natural logarithm of F over P divided by the natural logarithm of 1 plus R. Take for example, how long would it take to collect 1,300,000 if you invest 677,700 at an annual interest rate of 9 3/4%. Substituting this value to the formula, we obtain 7.0018, or approximately equal to 7 years. The rule of 72 and other rules. A general approximation can be used to find the time required for a principal sum to grow in certain multiple times. Rule of 72 estimates the number of years to double the principal when invested at rate R compounded yearly. Rule of 114 estimates the number of years to triple the principal when invested at rate R compounded yearly. Rule of 167 estimates the number of years to increase the principal fivefold
when invested at rate R compounded yearly.
To illustrate, at a time when the interest rate is 10%, it would take 7.2 years to double a principal sum, 11.4 years to triple it, and 16.7 years to have it grow fivefold. To double, here is to triple the amount, and to increase the amount fivefold. Consider the problem. How long would it take to have an investment amount to grow 30-fold if the interest rate is 12%? First, we analyze 30 into factors corresponding to our rules. Therefore, we have the rule to double, the rule to triple, plus the rule to increase fivefold divided by R. By substituting the values, the rule of 72, rule of 114, plus the rule of 167 divided by 12. So that is 353 divided by 12, or 29.4 years. Another problem. How many years would it take for a principal sum to grow by a factor of 12, given an interest rate of 8.5%? First, we analyze 12 into factors that corresponds to the rules. Therefore, n is equal to rule to double plus rule to double plus rule to triple divided by R. Therefore, we have n is equal to 72 plus 114 divided by 8.5 is equal to 258 divided by 8.5 is equal to 30.3 years. So the rate here is being used as whole numbers, not as percent. Nominal and effective interest rate. The interest rate stated in all financial transactions and documents is normally a nominal rate, denoted by J. That may also be referred to as the annual percentage rate. The effective interest rate is the rate obtained according to the conversion period used in the compounding process. The conversion period is the time between successive computations of interest. 1 for annual compounding, 2 for semi-annual compounding, 4 for quarterly compounding, 12 for monthly compounding, 52 for weekly compounding, and 365 for daily compounding. To indicate the rate is 8% compounded quarterly,
We may write 0.08, m is equal to 4 inside the braces. Consider an amount compounded quarterly at 8%. The nominal rate here is 8% and the rate per conversion is I is equal to 0.08 over 4 or 0.02. If a principal P is invested at a nominal rate J compounded more than once per year, the interest earned by the end of 1 year is greater than P multiplied by J. To illustrate, if 1 peso is invested at 8% compounded quarterly, the amount F and interest I at the end of 1 year are F is equal to 1 plus I raised to n, where I is 0.02 and n is equal to 4. So F is equal to 1.08243 and I is equal to 0.08243. The interest I, 8.243% of the original principal 1 peso, is the same as that obtained if 1 peso is invested for 1 year at 8.243% compounded annually. Clearly, compounding multiple times in a year will yield a greater interest. The effective interest rate is the rate obtained according to the conversion period used in the compounding process. If we denote the conversion period by M, we can calculate the effective interest rate W for any quoted nominal rate of interest J. Using the formula, W is equal to the quantity 1 plus J over M raised to m minus 1. If the nominal rate of interest stated is 6%, what would the effective interest rate be if the compounding occurs annually, semi-annually, quarterly, monthly, weekly, and daily? For annually, we have 0.06%. That is the same as the nominal rate. For semi-annually, slightly more than the nominal rate, which is 6.09%. For quarterly, 6.136%. For monthly, 6.168%. For weekly, 6.178%. For daily, 6.184%. Compounding according to number of conversion per year. If you invest 10,000 pesos at 7.14% interest for 3.5 years, how much would you accumulate if the compounding occurs annually, semi-annually, quarterly, monthly, weekly, and daily? For annually, we have F is equal to P times 1 plus R raised to N, or 12,775.87. For semi-annually, we have F is equal to 12,830.74. For quarterly, 12,859.24. For monthly, 12,878.66. For weekly, 12,886.22. For daily accumulation, we have 12,888.17. Suppose that it is possible for us to compound a principal continuously. The formula for the future value when an amount P is compounded continuously at rate R for T years is given by F is equal to P times E raised to R times T. We can also find the present value using the formula below by reversing the process. The present value is equal to F times E raised to negative RT. Historians believe that the first person to calculate E equals to 2.71828 was most likely a banker or trader exploring the properties of compound interest. By examining equation for compound interest, for a special case P is 1, T is 1, and R is 100%, we have F is equal to 1 plus R over N raised to NT, or F is equal to 1 plus 1 all over N raised to N. Mathematicians led by Jacob Bernoulli in 1683 would later go on to define E as the limit of 1 plus 1 over N raised to N as N approaches infinity, which is equivalent to 2.71828. Consider the problem. If you invest 10,000 pesos at 7.14% interest for 3.5 years, how much would you accumulate if it is compounded continuously? Using the formula F is equal to P times E raised to RT, we have F is equal to 10,000 times E raised to 0.0725 times 3.5, or F is 12,888.50. For the next example, a fund of 72,500 compounded continuously at a rate of 5.5% will be received in 30 months. How much would it be if it were to be cashed in today? Using the formula, the present value is equal to F times E raised to negative RT. We have P is equal to 72,000, E raised to negative 0.05
2.5 times 2.5 or 63,186 and 24 cents. Let us explore how continuous compounding be compared with daily compounding. For continuous compounding, we have f is equal to 12,888.50, while for daily compounding, we have 12,888.17. Although the principal amount of 10,000 is compounded continuously, as compared to daily compounding, it only gives a slight difference, which is equivalent to 33 cents. For your exercises, try the following problems.